Okay, I've started recording the session. Okay, this is a Zoom video conference, October 31st, 2019. I think everybody knows we have a test next Thursday and Friday. And so we'll be having a video conference on Tuesday before the test, and we'll probably be going over more items that might be on the test. First of all, does anybody have any questions about any homework problems or how to work any kind of problem that we've covered so far?
I think I'm trying to think which ones they are, but not the first probability, not the basics about probability, but the last two.
Basic probability?
No, not that one, but it's the other two after that one. But I mostly had issues on the last one.
Oh, counting and probability?
Yes, sir, I think so.
Okay, we're going to work some problems. If you have a particular problem you want to try to work, we can do that.
Okay, it doesn't matter. I just prefer you work whatever you want to work on.
Okay. What does everybody think about this this section we're doing now? Is it the hardest so far?
I mean, not really. You just have to be careful, you know.
You do. You have to know how to count and remember permutations and combinations. Let's look at a particular problem that's on the homework. This actually comes from the homework that I did myself, and I call myself a Robert Engineer. And so this is a question that evidently I got right because it's got 2 check marks. This particular problem, it says you got 10 different letters and you want to, how many words can be made, how many 3-letter words can be made from 10 different letters. Now this problem doesn't make a lot of sense because you really can't make any words that make any sense. But evidently FGH would be a word, for instance, from these choices. So if repetition of letters is allowed, and you're going to make the first letter, second letter, and third letter, you got a choice of 10 different letters for the first letter. And for the second letter, if you can repeat them all, in other words, you could have FF, then there would be 10 possibilities. And for the third one, there would still be 10. So the total would be 10 times 10 times 10 equal 1,000. So that's the answer if repetition is allowed. If the repetition of letters is not allowed, then you got, for the first letter, you got 10 possibilities. After you use that first letter, you got 9 left. And after you use that second letter, you got 8 left. So the total is 10 times 9 times 8, which is 720. Does that make sense? Now, I'm going to, here's a problem we're going to look at in a lottery game. A player picks 4 numbers from 0 to 9. How many different choices does he have if order matters, and if it doesn't matter, I'm going to work another problem before I work this one to sort of show what you would do if you're trying to work it out and write down all the answers. So I'll make it a little simpler. Suppose you have a daily game, a player picks 3 numbers from 0, 1, 2, 3. How many different choices does the player have if order matters? Well, if order matters, you're going to be picking 3 numbers from 0, 1, 2, 3. And so if we work order matters, let's just look at the various possibilities. And you'd go crazy trying to do this if you had 10 different numbers to write down all the possibilities. But we can actually do it if we only have 4 numbers. So let's look at the possibilities. Suppose you decide you're going to use 0, 1, and 2. So put down 0, 1, 2. And then you can say, well, that 0 could still stay first. And then you could switch the 1 and the 2 and go 2, 1. Then you could put that 0 in the middle and put the 1 and 2 on either side, and then switch the 1 and 2 again. And that would give you another combination. And then you'll say, well, let's put the 0 at the end and put the 1 and 2 at the beginning, and then switch the 1 and 2 to be 2 and 1. So this is the 6 that you can get if you're using 0, 1, and 2. Well, another possibility is to use 1, 2, 3. So let 1 go first, and then do the 2 and 3, and then 1 stay first and make 3, 2. And then let the 1 be in the middle and put the 2 and 3 on either side, and then switch them again. And then let 1 be at the end and put 2 and 3 at the beginning, and then switch them. And then you can use 2, 3, and 0. And so you do 2, 3, 0, 2, 0, 3, put the 2 in the middle and put the 0 and 3 on the sides, and keep on going. You got 6 possibilities there. Then the last possibility is to use a 3, 0, and 1. If you look at it, those are the only particular sets of 3s that you can use. So you do 3, 0, 1, 3, 1, 0, 0, 3, 1, 1, 3, 0, 1, 0, 3, and 0, 1, 3. And now you've used all the possibilities, and if you count all these up, there are 6 here, 6 here, 6 here, and 6 here, so there are 24. Now, if I ask you to do this problem where you got 10, you would absolutely go crazy trying to look at all the different possibilities of using 0, 1, 2, 3, all the way to 9 and writing them down. But thankfully, some mathematicians have come up with a formula, and it's called if order matters, and you've got n things taken r at the time, if order matters, it's going to be n things, n permutations taken r at the time, NPR. And so we can calculate that on our calculator if order matters. And I can bring the calculator up, clear it, and I want to do the permutations of 4 things taken 3 at the time is what I want to calculate. So bring the calculator back up and we will put 4 in, and we want to do probability, and we're going to do the NPR, the permutations. So we'll pick that, and it's going to be 3 at the time. Hit that, and it should give us 24. And we got 24. Now, if order does not matter, in other words, you're just getting 3 numbers that are unique, then can you anybody tell me how many it would be if order does not matter? Can anybody see that? You can see all the possibilities if order does matter. If order does not matter, how many are left? Jason?
Yeah.
Huh? How many would be there if order does not matter? In other words, having 0, 1, and 2 is the same as having a 0, 2, 1. In other words, you got those 3 numbers. Huh? I can't hear you.
24?
How many?
24.
No, if order matters, 24 is the answer. And you got the 4 different columns there. Now, if order does not matter, then you're going to cross out this, all of these have 0, 1, 2 in them, right?
So it'd be 4 combinations, wouldn't it?
That's right. Now we take these away, take these away, take these away, take these away, take this away, this away, this away, this away, this away, because they're the same 3 numbers. So it's 4. And by the way, that's going to be n things, combination of n things taken r at the time. In this case, it would be 4 things combination taken 3 at the time. And if you do that, we already know the answer is going to be 4. So that's, you don't always have to clear it, but I like to. 4 things, hit probability, and pick the combination, because that's where order does not matter. And 3, and that better give us 4. Now you can see how complicated it would get if you're going to pick from 0 to 9 and pick 4 numbers. If order matters, then you're going to use 10 permutations taken 4 at the time. In this case, we're picking 4 numbers out of 9. And so use your permutation if order matters. You got to remember that. And I'm going to do 10 I'm going to do the permutation, taking 4 at the time, and this is going to be 5,040. Now, if you had to do that on a sheet of paper, you would just never get it done, right? If you had to write down all the possibilities, you would have to really have a computer to do that, to run through all the permutations. Now, if order doesn't matter, it's going to be 10 hit probability. Uh-oh, hit the wrong thing. 10 hit probability combinations, 4 at the time, and it's 210. Still a lot of possibilities, especially because you have 10 numbers to pick from. So I was hoping maybe that would give you a little more insight in the difference between permutations and combinations. Now, this is a problem we did, I think, last week. It's a counting problem when you have choices for an administrative assistant, a software engineer, administrative assistant, and a sales representative. There are 4 possibilities for the software engineer, 4 for the position of administrative assistant, and the sales representative, there are 3. So the total is M times N times K. This is M, N, and this is K. M times N times K is 4 times 4 times 3 is equal to 48. Okay, number 13, we're going to be having to use combinations here. We've got 22 students, and they're going to pick 2 students that'll be selected at random to be in the fall play. What is the probability that no boys will be chosen? Order is not important. So first of all, we need to know the total number that may be picked. With boys and girls. In other words, gender doesn't matter. Well, that is combination of 22 students taken 2 at the time, okay? That's the total number of pairs that may be picked if a boy and a girl can be picked, or a boy and a boy, okay? So that is going to be 22 probability combinations taken 2 at the time equal 231. I would suggest, if you have your calculator with you, to follow along with me, make sure I'm not making a mistake. And then the total number of ways you can get 2 girls out of 12 possibilities. So that would be combination of 12, taking 2 at the time, is equal to we're going to do combinations taking 2 at the time equals 66. So the probability of 2 girls being picked is going to be 66 out of the total of 231. And let's see, that is, we can divide 3, you get 22 over 77. And we can divide 11 into that and get 2 sevenths. So the probability is 2 sevenths. Okay. Poker hand consists of 5 cards dealt from an ordinary deck of 52 cards. How many different hands are there consisting of 4 hearts and 1 spade? There are 13 hearts. In a deck. If you're going to get 4 hearts, that would be combination of 13 hearts, 4 at the time. That's a way to get 4 hearts out of 13, which is going to be has anybody there got a calculator they could put this in and tell me what it is?
I'm afraid not. I left mine.
Always bring your calculator. 13 combinations, taking 4 at the time, 715. Well, that's how you can get 13 hearts. So now you've got, how do you get 1 spade? 1 spade. There are 13 spades, and you want to see how many, obviously there are 13 possibilities there. That's 13, combination of 13 taken 1 at a time. That is obviously going to be 13. So the total possibilities is 715 times 13, which is 92.95. Okay. Now I'm just going to write down this. How many 4-topping pieces can be made from 13 individual toppings? That's just going to be combination of 13 things taken 4 at the time. And I'll just leave it to you to do that. I believe that's 715. I believe we did this one last week. If you're going to have 5 members on the board of directors, how do you pick a chairperson? You can pick one of the 5. So there are 5 possibilities. Once you pick the chairperson, there are 4 for the secretary. Once you pick the secretary, there are 3 for the treasurer. So you got 5 times 4 times 3 equals 60. Okay. You probably remember that this week we've been doing expected value. And when you do this, you have to look at all the possibilities, and for all the possible outcomes, you need to calculate the probability and then sum up the outcome times the probability and add them all up. Okay, so let's try to do this. A bag contains 2 gold marbles, 8 silver marbles, and 25 black marbles. That's a total of 35 marbles. So you're going to select, if somebody offers you to play this game, evidently it doesn't, you don't have to pay to play. So you don't have to put down $1 or anything. You just get somebody's going to let you take a chance without putting any money down. So what's your expected value? So we need to look at the outcomes. Pick a goal. The value of that, if you pick a goal, you win $4. What's the probability picking a goal? Probability of picking a goal is 2 out of 35. So another outcome is you could pick silver. The value of that is $3. And its probability, since there are 8 silver, is 8 over 35. And then you could pick a black. You lose $1. Okay, evidently, so you have to pay. You lose $1. And the probability of picking a black is 25 out of 35. So the expected value is going to be your 4 times 2 out of 35 plus 3 times 8 out of 25 minus $1 times 25 over 35.
That second one needs to be a 35 too.
Oh, you're right, thanks. 35. Always check your work. Okay. So now that's going to be so much over 35. That's going to be 8 here plus the 24 minus the 25. So that's going to be 7 out of 35, which is 0.2, which is what I had here. Does that make sense? You do this for just about any game you could play, whether it's a lottery or the casino. Let's do this one. Now this is when the Kiwanis Club is selling raffle tickets. A raffle ticket costs $2. There'll be one winning ticket worth $1,000, 3 tickets worth $100, and 5 winning tickets worth $20, and 1,000 tickets are sold. What's the expected value of one raffle ticket? Okay, I'm going to put. I had not worked this problem ahead of time. The outcome, the value, and the probability. Let's see if we can do this. The outcome is, suppose you win $1,000. If that's the outcome. If you win $1,000, now you paid $2. Let's see. Cost $2. So the value to you is $998. The probability of that happening is 1 out of 1,000, because there are 1,000 tickets sold. Now, you could also win the $100, and its value would be $98 because you paid $2 for the lottery ticket. I mean, for the raffle ticket. Its probability, there are 3 of those. And you could also win $20. Its value to you would be $18. And how many of those are 5? I'm not lining these up too good, am I? And then you could not win, in which case you're out $2. And the probability of that is 991 over 1,000. Does everybody see that? There are 9 tickets that would make you some kind of a winner. So there are 991 that could be drawn, which you wouldn't win. So expected value is equal to 998 over 1,000 plus 98 times 3 over 1,000 plus 18 times 5 over 1,000. And finally, minus 2 times 991 over 1,000. And if I had worked that, when I put the key together, that turns out to be minus $0.6 or 60 cents. Okay, the next problem is an expected value problem that I think is very interesting, and it's going to be a little involved, so I wanted to lay out things very carefully. Basically, this is a state's lottery that has 40 balls numbered 1 through 40, placed in a machine, and 8 of them are drawn at random. If the 8 numbers drawn match the numbers that a player had chosen, the player wins $1 million. In this lottery, the order in which the numbers are drawn does not matter. The first thing we're asked to do is to compute the probability that you win the $1 million prize if you purchase a single ticket. And we want to write this as a reduced fraction. What you need to do is calculate the combination of 40 things taken 8 at a time. And if you do this, put this in your calculator, just as we've done for the other combinations, you get 7, 6, 9, 04, 685. So the probability, if you buy 1 ticket of winning the lottery or winning the $1 million, is going to be 1 out of this large number. I'm not going to repeat it again. And now we have 2 questions. A single lottery ticket costs $2. Compute the expected value to the state if 10,000 lottery tickets are sold. Round our answer to the nearest dollar. Well, I'm going to work this on the next page. Notice that I put all the information up here as we work the problem so you can see all the parameters. Remember that the possible number of 8-ball combinations is this number. And so if 10,000 lottery tickets are sold, they're going to be this large number minus 10,000, which is 768,94685, that won't win. Okay. If these other 10,000, one of these other 10,000, which are sold, are picked, then there'll be a winner. So now let's look at the expected value to the state. The possible outcomes are that nobody wins. If nobody wins, the state made $20,000. And then the probability of that outcome would be this possible number of tickets that couldn't win. That's a large number that could be drawn minus the 10,000 that were sold. So the probability of nobody winning is this number, which is almost 1, but it's not exactly 1. The other outcome is somebody wins. And so the state has to pay out $1 million minus the $20,000 it got on the tickets. So it's out $980,000. The probability somebody wins is that one of these 10,000 tickets will be picked out of the total number of tickets. So then the expected value then is 20,000 times the probability that nobody wins, which is this number, minus 980,000 times the probability that somebody wins, which is 10,000 over this large number. And if you put that in your calculator, you'll get $19,869.97. Rounded off to the nearest dollar is $19,870. So that's the expected value for the state. Now we're going to calculate the expected value to the player if he bought 10,000 tickets. Notice it's going to be an interesting situation. Suppose he was the one who bought all 10,000 tickets. What is his expected value? So for the expected value to the player, which we outline here, possible outcome he wins, his value is $980,000. That's the $1 million minus the $20,000 he spent on the tickets, on the 10,000 tickets. The probability that he wins is the 10,000 tickets, or 10,000 numbers he bought divided by this number. And then the other outcome is he loses. And if he loses, he's just out $20,000 he spent on the tickets. And the probability that he loses is equal to the total number of possibilities minus the 10,000, which, by the way, is the same probability as we had up here of nobody winning. So now the expected value to the player is going to be the 980,000 times the probability that he wins, which is this, minus $20,000 times the probability that he loses, which is this number, which is almost 1. And when you multiply all this out, you get exactly the negative of the number we got before. This is how much he would expect, about 19,869.97, which rounds to 19,870. So if you look at the expected value of the player and add that to the expected value of the state, it adds up to 0, which is sort of a zero-sum game. Anyway, that's an interesting problem. Before we talk about just normal distributions, let's talk about probability distributions in general. The one possible way that random numbers can be distributed would be uniform. And they may be distributed between, say, minus A and plus A, where A is just a number. And the probability of a number being anywhere between here, they're equal probability. There's a triangular distribution that looks like this. And the number could be between minus A and plus A. And then there is a normal distribution, that's the bell-shaped curve that I know you've seen. And for the uniform distribution, the probability that a number is, say, there in the middle over a certain range is the same if a number being in this range, where the width of this rectangle is the same. However, for the normal distribution, the probability that a number is in the range of a certain width is higher right in the middle of the distribution than it is for the number to be a long ways away from the mean. By the way, use of X is the mean value. And it's the same for the triangular distribution. The probability of a number being in a range of a certain width is greater in the center than it is being in another range of the same width. Now, the area under the curve is always 1 for all distributions. In other words, all of the data is somewhere under the curve, 100% of it. So if you would take the area under the curve, 100% of the data is under the curve. 100% of the data here is under the curve. And even for the triangular, 100% of the data is under the curve. Now, the probability of a number being between, say, A1 and A2 equals the area under the curve. For instance, here is A1, here is A2. The probability the number is between A1 and A2 is equal to the area, this blue area here. And if it's a uniform distribution, if this were A3 and A4, with the difference between the two being the same, the width being the same. So we have the same probability over here on the right as we do on the left. However, for the normal distribution, an area between, say, A1 and A2 and A3 and A4, probability is much greater that it's between A1 and A2 than it is between A3 and A4. And the same goes for a triangular distribution. So now let's talk strictly about the normal distribution. The normal distribution is symmetric. It's bell-shaped curve with a single peak. The peak corresponds to the mean, the median, and the mode. If you look to the left of the mean, 50% of the data is on the left, 50% of the data is on the right. So the probability that a given value of X is more than the mean is 50%. Probability that X is less than the mean is equal to 50%. So here are some facts about the normal distribution. 50%, as I just said, 50% of the data values are below the mean, 50% or above the mean. Data values further from the mean become increasingly rare. That's because the curve goes down as you get away from the mean. The graph of the distribution is bell-shaped, as we said, with tapering tails that approach but never actually touch the horizontal axis. So as this curve gets closer and closer to the x-axis, it never touches but gets as close as you want to as the further you go out. Almost all the area under a normal distribution is within 3 standard deviations of the mean. And the total area under the curve, as we said, is 100%. So you need to understand these things about the normal distribution. And now we have what we call the empirical rule. And it's called the 68%, 95%, and 99.7 rule. So if you look at plus or minus 1 standard deviation, 68% of the data is between the mean minus 1 standard deviation and the mean plus 1 standard deviation. If you go 2 standard deviations out, turns out that 95% of the data is within that range. And if you go 3 standard deviations, you're up to 99.7% of the data. So you'll be able to have this curve on a test, so you'll be able to think through some normal distribution problems. Here's an example. Test scores on a math exam are approximately normally distributed with mean 72 and standard deviation of 8. Draw the normal curve and label the axes. Well, if the mean is 72, the next point is going to be 1 standard deviation above it, which would be 80. And the next one is going to be 88. And the next one is going to be 96. And you're going to subtract 1 standard deviation as you go to the left. And so what you will get is this. And the other thing I put here are the percentages. They're 34% here, 34% here, 13.5% here, 13.5% here. Notice, and then 2.35% between 2 standard deviations and 3 standard deviations. So we can get several things from this curve. The probability that X is less than 72 is going to be the area all the way over here is equal to 100%. I'm sorry, 50%. Or 0.5. Can somebody tell me the probability that X is between 80 and 85 and 88? In other words, the probability is between 80 and 88. Anybody want to take a guess?
That's not the 13.5%.
Yes, it is. If you see something that shows the area between 2 points, that's the probability. It's 0.1, it's 13.5%, or we would say 0.135. It's okay. How about the probability that X is between 64 and 48? In other words, between here and here. Anybody got a guess? What's that area there?
1540.
No, 1585.
0.85.
Which is 0.1585. Okay. So if you need to calculate probabilities, you look at the area between various points. Now, this particular curve is fine if things are on 1, 2, or 3 standard deviations. But suppose you wanted to know suppose you wanted to look at 76 and know the probability that is between 72 and 76. You'd have to know the area that I just pointed out, and you would have to get another curve that would tell you what it is. And there are curves that will do that. Question. This is on the practice test. What percentage of the data is between minus infinity and plus infinity? In other words, minus infinity is over here and over here. You know, you never get there. But what's the total percentage of the data? What did we just say?
%100%.
100%. Okay. Everybody needs to know that. Now, what's the probability that a data point will be greater than 2 standard deviations above the mean? And you should be able to do that by looking at this curve. Oops. What's the probability that's greater than 2 standard deviations above the mean? That means it's going to be out here. Does anybody see how to do that? There's enough information here to do that. you need to know the 2.35, right? Plus whatever is under the curve left out here. So you should be able to do that. What's the percentage from minus infinity to 2 sigma? In other words, from here to here. Can you count that up? What do we know? We know that 50% is to the left, right? So we got 50% to the left plus 34% plus 13.5.
So 97.5.
And see, did you add that up? 97.5. So how much has got to be left over here? We know it's got to be more than 235, right? It's going to be 100 minus 97.5, which is 2.5%. Does everybody see that? So we got 2.35% between 2 sigma and 3 sigma, and everything from 3 sigma on out to infinity adds another 0.15. Does everybody see that? You're going to need to be able to do that on a test. Okay, everybody try this one. The mean weight of a fish in a pond is 10 pounds. That means that this would be 10 pounds with a standard deviation of 3 pounds. Then this would be 13. This would be 16. And this would be 19 pounds. This would be 7, 4, and 1. So this is the distribution of fish in the pond. Plus the probability that a random fish caught is between 13 and 16 pounds. Now what we just had to do was we had to fill out the normal curve and then answer the question.
It would be the 0.135.
Exactly. The area under the curve is 13.5%. And so the probability is equal to 0.135. Okay. The other thing is a z-score. Is what you calculate if the data is not an integral number of standard deviations away. And so the z-score for a data point x is x minus the mean over the standard deviation. So find the z-score for a data value of 400. The z would be x is 400 minus the mean divided by the sigma, which is 50. This is minus 100 divided by 50 equal minus 2. And that means that the score was 2 standard deviations below the mean. Okay, the last one we're going to do here. Well, we've actually gone a little bit over time. A lot of times in a manufacturing plant, you have a specification for something you're manufacturing, like a roller bearing. It's supposed to be 2.2 inches. And you want the standard deviation of the bearings coming off the assembly line to be very small. In this case, it's 0.02 inches. Complete the distribution chart below. Well, if the mean is 2.2, that's what goes in the center. And then you go 2.22, 2.24, and then 2.26. And here would be 2.18, 2.16, and 2.14. And that's how you would fill that one out. Okay, I think will be all we'll cover now. We'll do more next Tuesday when we look at the test. Does anybody have any questions?
I don't. Thank you.
Anybody else have a question?
No, sir.
Okay. I will put this up on the web if anybody wants to relook at it, and for those who weren't able to attend this. I'm going to end the meeting now. You guys have a good week.
You too.
Thank you.